First of all, in order to understand the engine in general and to understand the cycle, when we have a cycle, it means you have Q hat added to the system, which is equal, or in general, Q hat minus Q cold absolute value equals to the work done by the system. So Q hat equals to the work plus Q cold. It means I give a quantity of Q hat, and as a result, we have a quantity of work omega plus a quantity of Q cold lost by the system. In order to understand this relation, I can give you a sample example of heat engine, okay? Or especially we talk about the vehicle engine. First of all, you have to know how the vehicle engine work, and from the initial point to the final point, okay? First of all, you know, we have the intake stroke. In the intake stroke, you have some quantity air is mixed with fuel. Here we have two valves, this one and two. Initially, the valves of this one is open. The quantity of air fuel mixture go inside this compartment. And here we have a crankshaft. We have a crank. You will get some rotation inside the engine. Okay. By this crank, you can have some work, omega. Okay, we have a motion. And here we have the second valve, where we have some quantity of heat goes outside the compartment, where we have Q cold. Okay, Qn and Q cold. We have Q hot and Q cold. And by the crank, we have some motion. So initially in the intake stroke, we have a mixture of gas and fuel inside the compartment. The piston goes down. In the second step, we have a compression stroke, where the air-fuel mixture is rapidly compressed up, as you see here, compressed up with the valves closed. It means these valves are closed, so we have a closed system. We can compress the gas with a closed system, okay? So the work is done on the gas. What I mean, we have a decrease of volume. In this case, the work is negative, okay? The work done by the gas is negative, but the work done on the gas is positive, okay? Okay, this is the second point. At the end of this point, when we have a maximum compression of the gas, we go to the power stroke. In the power stroke, where we have to ignite, or the air fuel mixture is ignited. Okay, here you have a spark, you have a bougie, to ignite the gas, the fuel, and in this case we convert the chemical potential energy, I mean the mixture of fuel and air, to the thermal energy. You get some quantity of heat, okay? This quantity of heat is Q hat added to the system. So by this operation, you can create a quantity of Q hat added to the system, okay? So when we have we have the ignition of the gas, in this case, this operation leads to a great increase in pressure. Okay, you got it spontaneously. You increase the pressure of the gas. So the piston descends and the gas does work by exerting a force F down. So here we have, we increase the pressure of the gas inside the compartment, and the gas will push down the piston. We increase the volume of the compartment. Okay, at this point, we have an increase of volume, so we have a positive value of work done by the gas. We can say we have a negative work done on the gas. Is the opposite of by the gas. Okay. Okay, this is the second point. We go to the final point. As a final point, we have the exhaust stroke, where we need to expel, we have to extract, to get out the hot gas to prepare the engine for another cycle. So we get out a quantity of heat, it's called Q cold, okay? And this piston will go back to the initial position. So from the initial position, initial step, from the intake stroke to the exhaust stroke, we have one complete cycle. We have Q hot added to the system by the ignition of the gas. We have Q hot. We have a motion of the crank. We have a quantity of work exerted by the crank. We have a motion. And at the last step, we have a quantity of heat lost by the system. So in general, we have Q hot added to the gas, which is equal to the work done by the crank, plus the quantity of heat lost by the system. So here we have an equivalence between the quantity of heat added, which will be divided to a quantity of work done by the crank, and a quantity of heat Q cold expelled, extracted from the gas at the final point. So the heat engines in general, you have to know the general map of the general operation of the heat engine. You have a high temperature T high, where we have the ignition of the fuel. We have a high temperature. This high temperature give a quantity of heat to the engine. Okay, the ignition of a mixture of fuel and air will create a high temperature. This temperature added to the system, to the engine, and the engine will do a quantity of work by the crank. Okay, and at the end we have a quantity of heat lost by the system, okay, to complete one cycle. Okay, so the external temperature, when we have when we extract the gas outside, we have an external medium, okay, where we have a temperature cold. So outside we have T cold, it's a low temperature as the final point. Inside, with the ignition of the gas, we have a high temperature T hot. The engine will gain this quantity of heat and will lose this quantity of heat, okay, and will do this quantity of work. So we have three parameters here for the engine. So in general, in the heat engine, we have Q hot absorbed by the gas, We have the work out exerted by the crank, by the engine, and we have a rejected quantity of Q cold outside of the system. Okay, so we have these parameters here plus T hot and T cold. These are the parameters of any heat engine: Q hot, Q cold, omega the work, and T high, and we can say T cold, T high or T hot. Okay, you can say here T high or T hot. Here you can say T cold or T low, TL. It's the same. Okay, and let me give you the first expression of the second law of thermodynamics. Here, if we have T hat, it means as we have a body, it has a temperature T hat. And here T cold, we have also a body or a reservoir with T cold. We have T hot and T cold. In general, the heat transfers of the heat in general occurs spontaneously from higher to lower temperature bodies, but never spontaneously in the reverse direction. So, in general, in the real process, you can go from the higher temperature to the low temperature, the heat, but you cannot go spontaneously from the low temperature to the high temperature. Okay, it's not reversible, it's irreversible. Okay, this is the first law of thermodynamics. Okay, here as you see, you can explain the situation like this. We have heat engine, we have hot reservoir with T hot, we have cold reservoir at T cold is the external medium, and the internal medium where we have ignition of the gas, and we have the heat engine. This engine, we have some quantity of heat Q hot enters the engine, and you have Q cold leaves the engine, and we have omega, the engine does work omega engine. So for any cycle, you have delta E equal to 0. From the first law of thermodynamics, we have delta E equals to Q minus omega of the cycle. So as delta E equals to O, we can say Q of the cycle equals to the work done by the engine. Okay, Q of the cycle equals to Q hot plus Q cold. As Q cold is a negative value, we can say minus times the absolute value. Okay, so we can say here Q hot equals omega of the cycle plus Q cold. Let me talk about the thermal efficiency of a heat engine. It means, okay, if in general we talked about this point, if we have a high value of Q cold, so we have a low efficiency. If we have a low value of Q cold, so we have a high efficiency. So for any cycle, we have to calculate the efficiency term, E. You can say E, or you can put it nu. Okay? As definition, efficiency equals to the total work omega cycle done by the gas divided by Q hat. In general, Q hat is a positive value. You can put it inside an absolute value or without absolute value. It's a positive value. Omega cycle, you know, if we have a clockwise cycle, omega done by the gas must be positive. In the case of anticlockwise cycle, omega done by the cycle is negative. Okay? In general, in the case of heat engine, you have to know, in the case of heat engine, we have a clockwise cycle. Okay? So here, omega must be positive of the cycle. So we have omega is positive, and you know omega equals to Q hat minus Q cold divided by Q hat equals to 1 minus Q cold divided by Q hat. Second point, all the heat engines expel only a fraction of the input energy by mechanical work. I mean, you cannot have a total, you cannot convert the total quantity of Q hat to a work because you have Q cold. Okay, just a quantity of heat is converted to the work omega, and the last and the other part will be Q cold. In this case, Q cold as a value is bigger than the than omega. You know, omega Q hat equals to omega plus Q cold. So in this case, Q hat is bigger than omega. In this case, E must be less than 1. It's a mistake here. Okay. So E must be less than 1. To have E equals to 100 or E equals to 1, Q cold must be equals to 0. But it's impossible to have 0 Q cold. It's impossible. Okay, so we would like, okay, we would like, but it's not impossible, it's not possible. We would like to have Q hat equals to omega cycle. It's the ideal case. All the quantity of Q hat is converted to the work, but this is impossible. So the second law of thermodynamics, second expression, it's impossible in any system for heat transfer from a reservoir to completely convert to work in a cyclical process in which the system returns to its initial state. Okay, so it's impossible to have zero Q cold. Omega of the cycle can never be equals to Q hot, means that Q cold cannot be 0, means that E cannot equal 100%. Okay, it must be less than 1. It's equivalent E less than 100%. Okay. So a simple example, here we have the hot reservoir where we have T high, T hot, and here we have a cold reservoir with T cold. We have 400 joule of Q hot added to the system. 100 joule of work omega, and we have 300 of joule as Q cold. This is a possible engine. This here we have an impossible engine where we have 0 Q cold. It's impossible. You can say here perfect heat engine, no energy expelled, so we have 100 of efficiency, but this one is impossible.